Today's topic is tangent planes. We're going to look at it in two ways. This is actually a fairly straightforward section. I've tried to not give a whole lot of problems on this because I just want to emphasize the main points. But there's two cases. One is if z equals f of x, y, surface, right, over some domain in the xy plane, is differentiable, then you can find the equation of the tangent plane, and this is it. You just memorize this. It's not too hard to memorize because it's similar to the tangent line formula you learned in Calculus 1, and we'll talk about that shortly. Then there's one more case. Sometimes a surface is given implicitly as a function of x, y, and z equals a constant, like your equations for quadratic surfaces were given that way, right? Or for spheres, these kinds of things. If you have a surface implicitly given, f of x, y, and z equals a constant, three variables in f, you can find the equation of the tangent plane of the surface from that also. That'll be equation 2 up here. But equations 1 and 2 will tell you the tangent plane for those two cases. All you need to know is those two things and the normal vector that comes out of each, and that's the whole section. So first we'll do this one. What should be a tangent plane to a surface z equals f of x? Why? Well, I'm going to claim this is what it ought to be, and here's why. If you rewrite this equation, z equals f plus partial of f with respect to x times x minus x0 plus partial of f with respect to y times y minus y0, all this at the point x0, y0. By subtracting all this over the left to right, 0 equals z minus f at x0, y0 minus fx at x0, y0 times x minus x0 minus fy at x0, y0 times y minus y0. This has the form, if you just multiply it out, right? This is a number because you plug in x0, y0, and this is a number, and this is a number. It's, well, subtract it over to the other side for this form. Minus z plus a number times x plus a number times y plus a number equals 0, right? So it's ax plus by plus cz plus d equals 0. This is the standard form for an equation for a plane, although sometimes d is put on the other side. But you can see instantly that when you write this out, it's a plane, right? It's a number times x plus a number times y plus a number times z plus a number equals 0. It's automatically a plane. And now you can do the following. If you plug into this equation of a plane, the point x0, y0, what do you get? Well, x0 for x makes this 0, y0 for y makes this 0, so you have 0 plus 0, you get z equals f of x0, y0. So this plane goes through the point on the surface, x0, y0, f of x0, y0 that you want. It goes through the point of tangency. Now, how do we know it's tangent? Well, you look at it and take the partial derivative of this function with respect to x, right? And plug in x0, y0. So partial derivative of a constant is 0. Partial derivative here with respect to x is 0. And so the partial derivative of z with respect to x is just 1 times fx, and this derivative is 0. All you get is 1 times fx. You get the partial derivative in the direction x. Similar, if you take the partial derivative of this function with respect to y, you get 0 plus 0 plus 1 times fy at x0, y0. You get the slope in the y direction. So this is the unique plane that passes through the point of tangency x0, y0, f of x0, y0, and has the correct slope in the x and y directions. That must be what we want to call the tangent plane. So we'll make this definition, if you like, that this is the tangent plane, and then we'll say it has those properties in it. It has the right slope in the x and y direction at the point of tangency. Now, what is the normal vector to that plane? And another way to describe this is by deducing it from the normal vector. That's the way I wrote it out here, actually. This plane is also normal to the perpendicular of the surface. And the perpendicular to the surface is just this vector right here. So minus partial with respect to x at x0, y0, minus partial with respect to y at x0, y0, plus 1. If you look, that's perpendicular. Let's move this up. To these two vectors that are tangent to the surface, right? This vector is tangent to the surface. If I move one in the x direction, my rise is the partial derivative with respect to x, right? The slope in the x direction is this, so one slope is the rise in the x direction. Similarly, 0, 1 slope is moving tangent in the y direction, right? If you move over 1 in the y direction, you have to move up by this slope in the y direction, partial derivative with respect to y. Well, if you take the dot product of this with this, right, you get minus fx plus 0 plus fx. The dot product is 0, so the normal, this n vector here is perpendicular to this vector that's tangent to the surface. Similarly, you take the dot product of this with this, you get 0 minus fy plus fy. You get the dot product is 0. So this vector is perpendicular to the vector within the tangent plane in this direction, in the y direction. And so this must be the normal because it's perpendicular to both vectors in the tangent plane. It looks like this. Here's the tangent in the x direction, the tangent in the y direction, and n is perpendicular to both, so it must be the normal vector. The other way to see it is just looking at the equation for the tangent plane. You can say, recall that any plane, ax plus by plus cz plus d equals 0, the a, b, and c are the components of the normal vector. Maybe you remember that from tangent planes. If you write this in the form ax plus by plus cz plus d equals 0, a plane in standard form, a, b, and c are the components of the normal vector, so you can actually just read them off from the equation here. It's off the top. But the equation had the coefficient of x was minus fx, the coefficient of y was minus fy, and the coefficient of z was 1. So this is automatically just reading from the equation the normal vector to that plane. All right, but this geometrically shows it nicely. There is how you can get a tangent plane when z is given as a differentiable function of x and y. You just immediately write down this equation, f of x0, y0 plus fx times x minus x0 plus fy times y minus y0. Here it is, you just write it down, and it has normal vector minus fx minus fy 1 immediately, which you can get by subtracting this over and looking at the coefficients of x, y, and z. All right. So immediately there's the equation of the tangent plane, there's the equation of the normal vector to any surface, and you really just memorize those. Otherwise you have to figure them out every time. They're not too bad. Oops. Let's try an example now. From those formulas, let's find the tangent plane to this nasty surface. Z equals square root of 4 minus x squared minus 4y squared. It's actually not such a nasty surface. I'll point it out down below again, but this is actually the top half of an ellipsoid. If you square both sides and run everything over to one side, except the constant, you can see it's an ellipsoid. And suppose I want to find the tangent plane at this point, x equals 1, y equals 1 over square root 2. Well, I need to use f at the point of tangency. So I plug in 1 over square root 2 into the function, and I get 1. I need the partial derivative with respect to x at the point. So here's the partial derivative with respect to x, right? You take 1/2, the argument to the minus 1/2, that's this times a half, and then multiply it by the derivative with respect to x, so what's inside? Well, right? 1/2 by the chain rule, 1/2 u to the minus 1/2 times partial derivative of u with respect to x is minus 2x. The 2 and the 1/2 cancel and you get just minus x over the square root. Try it yourself. This is the partial derivative with respect to x of this function. I plug in the point, 1 over square root 2, and with some calculations I get the slope of the tangent line in the x direction is minus 1. Similarly, partial with respect to y is 1/2 this whole thing to the minus 1/2 times partial with this respect to y is minus 8y. And the 8 partially cancels a half. You get this, minus 4y over square root 4 minus x squared. Minus 4y squared. Plug in the point, 1 over square root 2, and you get minus 2 square root 2 is the partial with respect to y at the point of tangency. And so now the equation 1 just says z is f at the point plus fx at the point times x minus 1 plus fy at the point times y minus 1 over square root 2. This is 1, my calculation up here, this one was minus 1, there, and this one was minus 2 square root 2, so it's just 1, minus 1 times x minus 1, minus 2 square root 2 times y minus 1 over square root 2. Multiply that out and regroup it, you've got z equals 4 minus x minus 2 square root 2y. There is the equation of the tangent plane. Z equals this linear function, ax plus by plus c. Right? In that form. Well, let's put it in the standard form. If I subtract, if I add x over and I add 2 square root 2y over, I can rewrite the thing in its standard form here. X plus 2 square root 2y plus z equals 4. X plus by plus c, z equals d. Or you can put minus 4 on this side if you prefer that other form. And then I wanted to point out, I told you this isn't too hard to memorize. Here's a good reason why. Do you remember from calculus 1 how you wrote the equation of the tangent line? It was very similar. Y equals f of x0 plus f prime of x0 times x minus x0. That was the equation of the tangent line to a curve y equals f of x at the point x0. Here's how you can show that, right? This is a number plus a number times x minus a number. It's of the form y equals ax plus b, so it's automatically a line of slope, whatever multiplies x, f prime of x0. So it's got the slope of the it's got the slope of the tangent to the curve, because right, take the derivative, it's f prime at x0, the same as the slope of the function. And it goes through the point, because you plug in x0, you get, this falls out, and you get f of x0, so it goes through, it's a line, ax plus b, through the point, because it contains x0, y0, with slope f prime of x0, y0, that must be what we want to call the tangent line. We did exactly the same thing, just back on the other page there, to find the tangent plane. We made it go through the point, we made it a plane, and we made it have the right slope in both the x and y directions, and we got this equation, z equals f of x0, y0 plus fx times x minus x0 plus fy times y minus y0. I hope you can read that, sorry. But this was the tangent plane. It's complete analogy. Look, it's just f plus derivative times x minus x0 plus one more term, derivative with respect to y times y minus y0. It's just one more term than what you had before. I had trouble remembering this until I thought of it that way. Maybe that will help you too. So it's the same formula. It's also called the local linearization we did last section, right? This was the local linearization. So that was really just the tangent plane we're finding. That makes it something maybe you already memorized, right? So, the tangent plane is the local linearization at the point x0, y0. Well, if you had enough, are you thirsty for more, as a famous young man once said. There's one more way to do this. That is the tangent plane to a surface given as z equals f of xy. Unfortunately, a lot of the surfaces that we do are not given in that form. They're like f of xy z equals c. This is the second form. Right? I said there's two ways to write an equation with a tangent plane. One of them is when c is given as a function of x and y. The other one will be when a function of x, y, and z equals c implicitly determines a surface, such as the ellipsoid we just talked about. Right? You could rewrite that ellipsoid in another form. I've written it below. Also the cones and the hyperbolic paraboloids, the elliptic paraboloids, all those things were given function of x, y, z equals a constant. That's how lots of these are given. spheres are given that way, right? Planes are also given that way. Of course, tangent plane to a plane is just the plane itself, so it's not as exciting, right? But here's what you can do for these. You remember the theorem last section, how important the gradient was, right? We said one of the applications was that the gradient of a function is perpendicular, orthogonal, to any level surface of that, right? So if I take a level surface of a function f of x, y, z, by f of x, y, z equals a constant c, right? That's a level surface. Just put the function equal a constant. Right? W equals f of x, y, z is something in four-dimensional space. And if you put f of x, y, z equals a constant, it's a surface in three-dimensional space that we call the level surface of this function, of this plot in four dimensions. So, since from last section, a normal to the level surface, f of x, y, z equals c, is the gradient at the point. Fx, right, and the gradient is the partial derivatives, fx, fy, fz, the three partial derivatives. We can find a normal to the surface to this thing just by writing the gradient at that point. So there's an even easier formula for the normal. It's just the gradient at the point is the normal. So now that immediately allows us to write the equation of the plane in point normal form. See, this is even easier than the last one we did. If this is the normal vector, a, b, c, and we go through the point, x0, y0, z0, remember the point normal form? It was a times x minus x0 plus b times y minus y0 plus c times z minus z0 was the point normal form. Let's just put this a, b, and c for an equation with normal a, b, c and point x0, y0, z0. We'll go back to the plane sections, review that, and you'll see that. And so just immediately from this, we can write down the equation of the tangent plane. This is provided that the function actually implicitly determines a differentiable surface through the point x0, y0, z0. So that's tacitly assumed in this formulation. All right. So now once again, we have a nice equation for the plane and a nice equation for the normal vector, this time when the surface is implicitly defined. So let's try and redo the last example, actually with it written in its standard form for an ellipsoid. If you square both sides and add stuff over, you get this equation, x squared over 2 squared plus y squared plus z squared, I'm sorry for the scribble, over 2 squared equals 1. This was the ellipsoid that we had solved for z in the last example. We solved for the top half of it, z equals the positive square root. Suppose we say, I know this point 1 over square root 2, 1 is actually on the ellipsoid. That's the other thing that has to be assumed. What is the tangent plane to the ellipsoid through this point that's on it? Right? And so we're doing the same problem as before, but it's going to be easier. Right? Because now this is an easier equation when we don't have to solve for z. The partial with respect to x is evidently 1/2 x. Right? This is of the form capital F of x, y, z equals a constant c. Right? So we're implicitly defining the surface of the ellipsoid, and the partial derivatives of given in this implicit form is 1/2 x. Partial with respect to y is 0 plus 2y plus 0 is 2y. Partial with respect to z is 1/2 z. And we plug in the point of tangency, 1 over square root 2, 1. We only need the x and y coordinates, well, for these two. Anyway, plug in x, plug in y, plug in z, and you find out the slope, the partial derivatives are 1/2 square root 2 and 1/2. So immediately from the point normal form, a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. With a, b, and c, the partial derivatives at the point is 1/2, right, this one, times x minus 1 plus square root 2 times y minus 1 over square root 2 plus 1/2 times z minus 1 equals 0. When you multiply that out in group, you get the same equation, and multiply through by 2 and multiply out in group, you get the same equation as before, 2x plus 2 square root 2y plus z equals 4. Easier than the other way, right? So sometimes it's easier just to leave these in their implicit form and do it. that way. Well, let's try just finding the normal vector, the normal line, I'm sorry. Some of the problems are find the normal line of the surface going through the point of the tangent plane. Well, we can easily find that because we just wrote down the equations for the normal vector as 1a and 2a to go with one of those 1 and 2 for the two tangent planes. For instance, if z equals the ellipsoid in this form from the first example at the point here, the normal vector is immediately, we wrote it down, minus fx minus fy1. These were just the coefficients of that came out in the equation, right? So minus fx minus fy1 was the normal from which we deduced the equation. And so you just plug in the point, 1 over square root of 2, and you get minus a minus 1, minus 2 square root of 2, 1. You get this normal vector 1, 2 square root of 2, 1. And if you get it, if you give the surface implicitly, remember the normal vector was just the gradient, fx, fy of z, plug in the point, and we get the vector 1/2, square root of 2, 1/2. And so, either way, you can use either normal vector, it doesn't matter. How do I find the equation of the tangent of the line normal to the surface through the point 1 over square root of 2, 1. I just use either normal vector, and I use the point through which it goes, and I write down the equation for the normal line, and you just have to remember what that was. The normal line, or a line with a given direction, n in this case, through a given point, x0, y0, z0. So if you have a vector ABC, that's the direction of the line, and a point x0, y0, z0, on the line, you immediately write down parametric equations for the line. X equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct. Remember parametric equations for a line? These were the parametric equations when the line was in the direction of ABC going through the point x0, y0, z0. So you just immediately write these down because you already have the normal, and so we'll use this one B here. It goes through the point 1 over square root of 2, 1. That's your x0, y0, z0. Your direction is 1/2, square root of 2, 1/2, and you just write those in immediately. There's the equation of the normal line, easy as could be. Try these problems. In problem 13, it asks you to find all points at which the tangent plane is horizontal. What you do for that is you just have to find what the normal vector in the vertical direction, up or down, and see what that imposes on